Assalamu alaikum students. I hope you are all fine by the grace of Almighty Allah. I welcome you all to the third lecture of Thermodynamics 2. This is our third lecture. The contents of lecture 3 are forms of energy, mechanical energy, energy transfer by heat, energy transfer by work, heat versus work, ideal gas equation for different processes, work done for different processes, polytropic index for different processes. Specific heat and latent heat. What is specific heat? It is the amount of heat required to change the temperature of unit mass of substance by 1 degree or unity. The formula of specific heat is C is equal to Q, that is heat, divided by mass and change in temperature. The unit for specific heats are joule per kg per Kelvin or kilojoule per kg per Kelvin. Now, you have to remember that specific heat depends upon the process followed by the system. So, for gases, there are two values for specific heat: specific heat at constant pressure and specific heat at constant volume. And you also have to remember that the specific heat for constant pressure is always greater than specific heat at constant volume. For solid and liquids, as they are incompressible, so that's why they have only one value of specific heat. Specific heat and latent heat. Latent heat. The verbal meaning of latent heat is it is a hidden form of heat. So the definition is amount of heat required to cause a phase change in unit mass of substance at constant pressure and constant temperature. As it is a phase change process, therefore during the process the temperature remains constant and all the heat supplied is utilized for the phase change process. The formula for latent heat is L is equal to Q divided by M, where Q is the amount of heat supplied. The units for latent heat are joule per kg or kilojoule per kg. There are two types of latent heat. Latent heat of fusion, which is represented by LF. As the name suggests, the process fusion is the conversion of solid into liquid. So the definition of latent heat of fusion is it is the amount of heat transferred to melt a unit mass of solid into liquid or to freeze a unit mass of liquid to solid at constant pressure and temperature. The formula to calculate latent heat of fusion is LF is equal to QF divided by M, where QF is the amount of heat supplied for the process of fusion. The units of latent heat of fusion are joule per kg or kilojoule per kg. The second type of latent heat is latent heat of vaporization, which is represented by LV. As the name suggests, vaporization, it is the process of conversion of liquid into vapors or gas. The definition of latent heat of vaporization is it is the amount of heat transferred to vaporize a unit mass of liquid or to condense a unit mass of vapor to liquid at constant pressure and temperature. The formula to calculate latent heat of vaporization is LV is equal to QV divided by M. QV is the amount of heat supplied for the vaporization process. The units are joule per kg or kilojoule per kg. Internal energy. Internal energy, it is the sum of all forms of microscopic energies. The mathematical representation of internal energy is capital U. So the internal energy is the summation of all forms of microscopic energies. These microscopic energies include translation energy, rotation energy, nuclear energy, electronic energy, etc. For ideal gas, there is no intermolecular force of attraction and repulsion. Here we have to remember that the internal energy is the function of temperature only. So if the temperature is increased, that implies that internal energy will also increase, or if there is a decrease in the temperature, this implies that the internal energy will also decrease. So here is a proof that usually asked in the examination, that prove that internal energy is a point function. We have previously studied there are two types, point function and path function. So here we have to prove that internal energy is a point function. So internal energy depends on initial and final state of the system, and it is independent of the path of the system followed by the process. It is the property of the system. So on the right hand side, you can see two different cyclic processes are shown. That is state 1 and that is state 2. In path process A, the change is from state 1 to 2. In B, the process is going from state 2 to 1, and in also C process, the process is going from state 2 to 1. In path A, the pressure is reduced from P2 to P1 and volume is increased from V1 to V2. And you can see that in path A, state 1 to 2, pressure is decreasing and volume is increasing. Whereas in path B, the volume is decreasing and pressure is increasing from P1 to P2. And also in path C, volume is also reducing from V2 to V1 and pressure is increasing. So for path A, from first law of thermodynamics, QA is equal to change in the internal energy in path A plus work done during path A. QA is equal to del UA plus WA. And for path B, QB is equal to change in the internal energy for path B plus work done for path B, WB. If we assume that we merge both path A and B and for cyclic process A, B. So as it is a cyclic process, so change in internal energy will be 0, and from first law of thermodynamics, all heat supplied is equal to work done. So QA plus QB is equal to WA plus WB. So WA will go into the left hand side and QB into right hand side. So it becomes QA minus WA is equal to QB minus WB. So del UA is equal to minus del UB. So change in internal energy for process A is equal to negative change of internal energy for process B. As it's a cyclic process, so the internal energy will be equal. Now for cyclic process AC, it is cyclic process from first law of thermodynamics. Summation Q is equal to summation W. QA plus QC is equal to WA plus WC. WA will come on the left hand side and QC will go on the right hand side. So it becomes QA minus WA is equal to WC minus UC. As we know that left hand side and right hand side represent the internal energies of the path. So del UA, its internal energy for path A, is equal to negative of del UC, internal energy for path C. So in the previous slide we have proved that UA, internal energy, is also equal to negative of internal energy for path B. So all these are equal. So here we have to note that it is proved that internal energy is a point function. It is the property of the system and it is exact differential. So you can find the value of internal energy at state 1 and state 2. Enthalpy. Enthalpy. Internal energy of fluid along with the flow work is called enthalpy. The significance of enthalpy is an open system is same as significance of internal energy in the closed system. It represents the total energy content of the system. We represent enthalpy with capital H and the unit of enthalpy are kilojoule. It is an extensive property. In the previous lecture, we have already studied about what are intensive properties and what are extensive properties. So the enthalpy is an extensive property, whereas specific enthalpy, which is represented by small h, whose unit are kilojoule per kg, is an intensive property. So if you don't remember what are intensive properties, what are extensive properties and what are specific properties, I'll suggest you go to the previous lecture and study them. Go through them so you remember them. So the specific enthalpy is represented by small h and the formula for specific enthalpy is H is equal to U plus PV, where U is the specific internal energy, P is the pressure and V is the specific volume. The unit for specific enthalpy are kilojoule per kg. It is the point function and exact differential. So as it is a point function, so it is a property of the state and you can find del H by H2 minus H1. heat transfer for various processes. So the first process is isochoric process. So we know that the isochoric process is a constant volume process. The formula for work is PdV. So according to first law of thermodynamics, Q is equal to del U plus W. As for constant volume process, the dV is equal to 0, so the value for work is also 0 as indicated by this arrow. So heat transfer for constant volume process is equal to change in internal energy. The formula for capital U is mCV dt. Therefore, heat transfer in isochoric process is equal to change in the internal energy. The second process is isobaric process. Isobaric process is a constant pressure process. According to first law of thermodynamics, del Q is equal to change in internal energy plus work done. Work done is represented by PdV. So we put the value for work done here. Del Q is equal to del U plus del PdV. For exact differential, we can replace the del sign with d. dq is equal to du plus dpv, as u and pv both are state functions, property of the system. Therefore, the differential sign can be taken outside. Change in energy is equal to change in internal energy plus change in pressure volume. So dq is equal to dh. Capital H is the enthalpy. So we have studied in the last slide that capital H is equal to U plus PV, and small h is equal to specific internal energy plus pressure into specific volume. So don't confuse by capital H and small h, as they are not the specific properties. Therefore, the enthalpy is not specific enthalpy. This is normal enthalpy. So the formula for enthalpy is mass into Cp dt, that is specific heat at constant pressure. Therefore, heat transfer in isobaric process is equal to the change in enthalpy. So in the previous slide we have studied this. For isochoric process, the change heat transfer is the change in internal energy, and for isobaric process, heat transfer is equal to change in enthalpy. Isothermal process. Isothermal process is a constant temperature process. According to first law of thermodynamics, del Q is equal to del U plus del W. This is the formula for internal energy. We have discussed this formula in the previous slide as well. Del U is equal to mCV del T. So here you have to remember that as this is the isothermal process, so the temperature during the process will remain constant and the value of del T will be equal to 0. So as the value of del T is equal to 0, so value of internal energy is also equal to 0. We put the value of 0 here, so del Q is equal to del W. and the formula for work done is PdV. Therefore, heat transfer in isothermal process is equal to work done. The statements which are written in red box are very important. Usually they are asked during the MCQs portion of examination, that what is the value of heat transfer in isothermal process, and there will be 4 options written and you have to select the right one. So the heat transfer in isothermal process is equal to work done. I have highlighted this information to make sure that you know that that is an important statement. So heat transfer for polytropic process. As you know that the expression for polytropic process is PV gamma is equal to constant. So according to first law of thermodynamics, del Q is equal to del U plus del W. This is the formula for internal energy. We have replaced it and we have derived this expression. Work done for polytropic process is equal to this. So del Q is equal to mCV dt plus P1V1 minus P2V2 n minus 1. We have already derived this expression in lecture 2. So if you have any confusion regarding how this expression was derived, you can go to lecture 2 and revise that. So in the next step, del Q is equal to m r over gamma minus 1. So how CV, right? There are basically two expressions, Cp minus Cv is equal to R and gamma is equal to Cp over Cv. When we combine, we will, from this expression, Cv is equal to gamma Cp. I will write here. So value of Cp is equal to Cp over gamma is equal to Cv. So we put the value of Cv here and then the value of Cv is achieved as Cv is equal to R over gamma minus 1. So you know that how that Cv was transformed into R over gamma minus 1 del T T2 minus T1 plus work done for polytropic process. So now for mRT2 from ideal gas equation, PV is equal to mRT. So mRT2 will become P2V2 minus mRT1 will become P1V1, and that right side expression, right side polynomial remain the same. Now I have changed the outline boundary for to different color so that student may not get confused. So the next step is here P2V2 minus P1V1. Here we have multiplied and divided with the n minus 1 plus right hand side remain the same. we have taken the P1 V1 minus P2 V2 over n minus 1 term common, and the other is inside the brackets. So now we know that Q polytropic, heat transferred in polytropic process, is equal to work done in polytropic process multiplied the expression in the bracket. Now what this expression suggests, that work done for polytropic process is always greater than heat supplied in the polytropic process. This is also very important statement. So when you are solving any problem and your answer suggests that heat transferred to polytropic process greater than work done, then your answer must be wrong, because you have already proved that the work done in the polytropic process is always greater than heat supplied during the polytropic process. Now, according to the first law of thermodynamics, del Q is equal to del U plus del W. So change in internal energy is equal to change in heat transfer minus work done. So as we have proved here, W polytropic is greater than Q polytropic. So as the second term is greater and the first term is smaller, so the answer for del U is negative. In polytropic process, when we add heat in the system, the temperature of the gas is decreased. Now we have to find an expression for specific heat for polytropic process, which is represented by C poly. This expression was already derived in the previous slide. Q polytropic is equal to W polytropic into gamma minus N over gamma minus 1. P1 V1 minus P2 V2 divided by N minus 1 into gamma minus N divided by gamma minus 1. So, MR T1 minus T2 over N minus 1 into gamma minus N over gamma minus 1. Now what we have done here is that we have changed the position. We have taken the minus sign out and you see that T2 and T1 are interchanged. So this expression was also derived in the previous slide, how Cv was converted into R over gamma minus 1. So Q polytropic is equal to minus M Cv T2 minus T1 into gamma minus N over N minus 1. So here we have taken the expression for C polytropic is equal to minus Cv into gamma minus N over N minus 1. As you know that Q is equal to mCp dt. M is positive. Heat always travel from high temperature to low temperature, so this factor decide, that is the deciding factor. Now as there is a minus sign, so the value of C poly is negative. So the statement we have proved in the previous slide is assured here. Temperature of gas decreased when we add heat in the system. So you may ask to derive the specific heat expression for polytropic process in the examination. So now we will solve a numerical. It's a numerical problem 1. The statement state, consider a system gas in the cylinder as shown in the figure. It's a piston cylinder system. It's a Bunsen burner. At the bottom you can control heat from this valve. So there is certain gas in the cylinder, and that is a piston, and some weights are on the top of the piston, placed at the top of the piston. So the statement, we will continue to read the statement. The cylinder is fitted with a piston on which a number of small weights are placed. The initial pressure is 200 kilopascal. So we will highlight the important information. The initial pressure is 200 kilopascal and the initial volume of gas is 400 0.04 meter cube. So the part A of the question states that if a burner is placed under the cylinder and volume is to increase from 0.04 to 0.1 meter cube. So this is initial volume and that is final volume for part A. Then calculate the work done by the system during this process while the pressure is constant. So the first thing while you are solving the numerical problem is to highlight the important information or to underline it. I have made the color of all the important information different in this statement, so you can highlight or underline the important information in the statement of the problem. So work done, the formula for work done from state A to 1 to 2 is integration from 1 to 2 P dV. Know that. Now the pressure is constant, therefore P comes out of the integration and dV. The change in volume is from 0.04 to 1. So final minus initial volume 0.1 minus 0.04. The initial pressure was given. So work done is 12 kilojoule. So you have to be very careful with the unit as well. If the pressure is in kilopascal, so the unit is kilojoule. Part B of the numerical problem. Consider the same condition, but at the same time the Bunsen burner is under the cylinder and the piston is rising. Remove the weights from the piston at such a rate that during the process temperature of the gas remain constant. So again this is a piston cylinder system and these are some weights. You have to remove the weights very slowly and allow the piston to rise. So the temperature of gas remain constant. So which is the process in which the temperature of the gas remain constant? It is a isothermal process. So the formula for work done is integration P dV, and this relation is, we have already derived this relation for work done. So relation for work done for isothermal process. So we just have to insert the values from the problem statement. Initial volume is 200 kilopascal. Initial pressure is 200 kilopascal. Initial volume is 0.04 meter cube. Natural log V2, final volume is 0.1 and the initial is 0.04. So the work done for isothermal process is 7.33 kilojoules. Part C of the numerical problem 1. Consider the same conditions, but during the heat transfer remove the weight at such a rate that the expression is PV power 1.3 is equal to constant. So you have to remember that PV n is equal to constant. It is an expression for polytropic process where the value of n is 1.3. So the expression for polytropic process is P1V1 n, here you can n, P2V2 power n. So P2 is equal to P1 V1 over V2 power n, and the value of n given is 1.3. When you insert all these values, the P2, the final pressure is 60.77 kilopascal. So we know the value of initial pressure, initial volume, final volume, and now we have calculated the value of final pressure as well. Now the expression for work done is P dV integration, and this relation we have derived this relation for work done for polytropic process in the previous lecture. So we will insert the final pressure, final volume, initial pressure, initial volume, value for n, and the work done comes out to be 6.41 kilojoules. Now we will solve another numerical problem. The statement of the numerical problem is: a cylinder fitted with a piston has an initial value of 0.1 meter cube and contains nitrogen at 150 kilopascal at 25 degrees centigrade. The piston is moved compressing the nitrogen until the pressure is 1 megapascal and the temperature is 150 degrees centigrade. During this compression, process heat is transferred from the nitrogen and the work done on the nitrogen is 20 kilojoule. Determine the amount of this heat transfer. First, we will underline the important information. Initial volume, initial pressure, initial temperature, final pressure, final temperature, and the amount of work done. Now, from first law of thermodynamics, del Q is equal to del U plus del W. It is the specific internal energy. So capital U can be replaced by m into small u. For state 2, as we have in the same lecture, we have proved that the internal energy is a point function. So internal energy for specific internal energy for state 2 minus state 1 plus W1 to 2. U is equal to CVT2. So we also proved that same. Q1 to 2 is equal to M CVT2 minus CVT1 plus W1 to 2. As specific heat at constant volume is constant, so we took out the value out of the bracket and the expression becomes Q1 to 2 is equal to MCV into T2 minus T1 plus work from 1 to 2. Now to find the mass we will use the equation of state. We have to find the mass, so we know that from equation of state PV is equal to mRT. Mass, we will take out the mass on one side and all other variables on the right hand side. We know the value of pressure, volume, R and T. So you will have to go to table A.5 at the end of your book, and in the table you will find the value for nitrogen. This is value of R for nitrogen and value for CV for nitrogen. So at the end of your book there is table A.5. So these values: specific gas constant and CV, you will have to take these value from the end of your book. Either these value will be given to you in the statement, or if you are solving, so you can find these value for different type of gases in the table A.5. So you will find the mass, which comes out to be 0.1695 kg. You will insert the value of mass, and the value of CV is from the table indicated by arrow, and you will find the amount of heat, that comes out to be minus 4.2 kilojoule. So the negative sign indicates that heat is taken out from the nitrogen. Perpetual motion machine of first kind, that is for information only. You might be asked in the interviews, what is perpetual motion machine of first kind? So a hypothetical machine which can produce useful energy, work without any source, or which can produce more energy than consumed. So first you have to remember that it's a hypothetical machine. It is an ideal machine which we cannot make. It is a hypothetical machine because from the law of conservation of energy, energy can neither be created nor be destroyed. So the perpetual motion machine of first kind suggests that useful energy can be produced without any source. So it violates the first law of thermodynamics. So if you are asked what is perpetual motion machine, so you will say that is a hypothetical machine which violates the first law of thermodynamics, because it can produce energy without any source. That is not possible. So that is a pictorial view of perpetual motion machine of first kind. You are seeing that there is no input source. This topic is more of MCQs and interview type question topic. So I have included that you can read some information regarding this topic. So you must know what is perpetual motion machine of first kind. In the upcoming lecture we will also discuss about what is the perpetual motion machine of second kind, what is the perpetual motion machine of third kind. These are very useful information and might be asked during the interview question. So home assignment of lecture 3. All students are advised to go through example problems of each topic discussed in this lecture. All students must submit handwritten lecture summary report minimum of 3 pages before the commencement of next lecture. This is very important. It must be handwritten and you have to submit it. So how can you submit? You have to take picture and scan the report and send it to my email address arsalan@ciitwa.edu.pk. You have to keep hard copies safe with you. So the examination will be conducted in the university, so you can bring them with you and submit them when you will come to university for the examination. All students are advised to prepare the previous lecture thoroughly before the online video session. So you must go through this lecture. If you don't understand, you can go through it twice, and you can also consult the textbook as well. And you must prepare before the online session, as you may be asked oral question answer individually. So handwritten report, send it to my email ID and prepare the lecture. Okay, thank you very much, students. Keep safe, uh, keep yourself safe and other as well. Thank you.